Hi, this is lecture 25 of integrable to 3. So we have seen from the beginning, we have seen subsets of R, then we have seen functions of R, then we have seen two classes of functions. One is the continuous functions, one is the differential functions. Now we will see another kind of functions that are of interest for us in this course. So let us recall what we have done for subsets of R. We have made some constructions and we have used that to distinguish some special kind of sequences. So before that, what we have done is, suppose I have a bounded subset of R, this BR, let us denote this to be bounded subset of R. BR is power set of R. This BR denotes a set of all bounded subsets of R. Now on these two, we have introduced two maps, infimum and supremum. These two maps we have introduced to serve some purpose. What is the purpose? Using these two, we were able to write down some description for some elements of R, some special elements of R. For example, root 2, it's not the very first description that we know of root 2 is this root 2 is supremum of some subset of R. What is it? X belongs to R positive, such that x square is less than or equal to 2. For this subset of R, this is how we have defined that we have seen that this is a subset that is bounded above. Then we have said, so because we are dealing with subsets of R, supremum exists for that, and the supremum we have mentioned it as root 2. We have proved that this element is such that the square of this element is 2. So that element we are denoting by root 2. So these two maps one can also use, one can also replace this by something else and put infimum here, you still get root 2. So these two maps are used to introduce some new elements of R. This is one example. This we have done this for bounded subset of R. Now for bounded sequences in R, unfortunately I am denoting that by still BR, maybe I will put some S here. Let us denote this to be bounded sequences in R. So SR was a notation for a set of all sequences in R, BSR set of all bounded sequences in R, sequences in R that are bounded both above and below. Now for this we have again introduced two maps. Here for bounded subset of R we have mentioned the infimum supremum. For bounded sequences we have two maps. What is it? Lim_inf and lim_sup. This is bounded sequences to R to R. To be precise, to talk about infimum, the subset need not be bounded above, but as I said, for our convenience we will assume that infimum is defined for bounded because we want some other properties for of infimum to satisfy. Infimum minus A is something related to supremum of A. So for that, for the definition we do not need this set to be bounded above, but we will just give that take the liberty and say infimum is defined on BR, supremum is defined on BR. So we are only considering the subset of R, subset of subset on which infimum is defined. Infimum is defined on this subset, the bigger subset, but we are focusing only on this. That is the point. Now let us come back to this. So for sequence also we have introduced two maps, and then what we have said is, suppose there is a sequence A or AN such that image of this map under image of this element under this map is equal to image of this element under this map, in the sense lim_inf of AN is equal to lim_sup of AN. Then we have called, I mean this is not the definition, but we have seen, suppose this is the case, then AN is a convergence sequence. again let me repeat, for bounded sequence in R we have these two maps. Now starting the bounded sequence, one can talk about lim-inf and lim-sup. Suppose they are same, then we know that it is a convergence sequence, it converges to this element. I mean these two are same, so yeah, so I can just declare this as the limit of this sequence. So there are two ways to do. One is the epsilon n. For function we have epsilon delta, right? So for sequences I am calling this this as epsilon n definition. That means given epsilon positive, there is n belongs to n, such that after this n there is some property. Suppose this goes to L, then a n minus L is less than epsilon, like that. So this this definition I am calling that as epsilon n. This equivalent condition I am calling as lim-inf lim-sup. So we will extend this idea. See, here we are defined only for bounded sequences in R. So it's a map A from N to R that is bounded. For those we have defined these two maps, and then using this we have other characterization for convergence sequences. Now let us do the same thing for arbitrary functions. So here we are focusing to the case where the domain is n. So let us extend the idea to more general subset of R. So let us take A comma B subset of R, and the f from A comma B to R is bounded. See, the previous experience says it is better to start with the bounded sequences, in case of lim-sup. In case of functions, it is better to start with the bounded, the function is bounded. Similarly here also we have done the same thing, right? Infimum supremum is defined only for bounded subset of R. So further reason, if you are trying to use this idea, then it is better to be the starting point should be that the function is bounded function. So that is what you are starting with. Now for this, again the same idea is to do the following, that somehow define, it may not be lim-inf because we are not dealing with sequences, somehow define two maps, and let me denote set of all bounded functions on AB by this. See, this may be very bad notation, I am using B for sequences, functions and all that, but forget about the previous thing whatever I said, there is notation, at least just notation, forget the notation. So for now this is set of all bounded functions on this local interval AB. Now again the same idea, whatever I have done for sequences we will do the same thing for this also. So we will define two maps whose domain is this bounded subset of bounded functions on AB, and then say suppose there is element f belongs to this such that L of f is equal to U of f. Then see, previously what happened, if I have a sequence an and the image of an under this and this are same, then we have seen that this is same thing as saying that this is a convergence sequence. So similarly, once we define these two maps and there is a element f belongs to BAB such that L of f is equal to U of f, then that should be special, and the speciality is what we are calling as, in this case we call f to be integrable, or maybe to be precise Darbox integrable, because these maps that we define, the first map is called lower Darbox sum, the second map is called upper Darbox sum. So we will define what is that and what are the properties and all that we will see. Now to talk about these maps, see what we have done in case of sequences. So we take some sequence an, then to talk about lim-inf, we have fixed the point A1. From there we have taken the supremum of the image of the sequence. Then as the next step we have taken element from A2, then taken supremum of the image of that sequence that is from A2, and then we did further. Oh, it is infimum, so we should take infimum. For supremum we should take supremum. So here we will do something like that. So given a function f, we will assign 2 elements of R. So to proceed in this way, we need the notion of what is called a partition. So starting with a bounded function a comma b to R is bounded. For this bounded function, to talk about these two maps, we need the notion of what is called partition, whatever I said just now. So what is a partition? Take this interval AB. A partition is a finitely many, is a subset of AB first of all, and that this is finite. So say x1, x2, x3 dot 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 xn minus 1. So a partition on AB is a finite subset of AB, that is all, finite subset of this interval AB. And we need extra, we need to have an extra data. What is it? That finite subset should contain both A and B. So a partition is of this form: A is equal to x0, x1, xn minus 1, xn is equal to B. So this will contain A and B, and I said that there are finitely many elements. So if there are finitely many elements, I know how to order them. So the first element I am ordering as x1, and the next bigger element I am ordering as x2, and so on. So this is how I am denoting elements of the partition. This is x0. Now what? Now I am trying to make use of the notion of infimum and supremum. See, I said that f is bounded function. So f of the image of f is bounded. So further I can talk about infimum, supremum, but that is not sufficient. See, whatever we have done for sequences, if you remember, we have not taken supremum of the whole sequence. We have done some steps. First supremum of the whole sequence, then removing the first element we have taken the supremum, then removing the second element we have taken the supremum. So like that we have done. That is what is lim sup, and then we have taken the limit of limit of the corresponding sequence. We will do the same thing here also. It is not a good. It is not useful to just consider limit of the supremum of the whole image. That is not what we are trying to do. See, one thing to do is take supremum of AB. This f is bounded function, and so for this we can talk about supremum and also infimum. That's not what we are doing. We are doing in the same way that we have done for sequences. We take some partition and we take supremum for this separately, and then add it up using some extra factor. What is it? So given a partition P for the function f, we have what is called lower Darboux sum of f with partition P. How is it defined? What I am doing is simply the following. I am just taking this, I am restricting f to this interval, then I am taking infimum of f restricted to a comma x1. This is what I am doing. So when I am doing something like this, I am assuming that at least for this partition, for this fixed partition P, this is almost giving a so I am trying to approximate the f in this partition, in this subinterval with this. So I am assuming that f is actually taking this minimum value in a to x1. So it is like a constant function. So I have to multiply this with the length of this. So I should also remember how much subset of R, subset of AB we are taking. So the how much means this length. So this is x1 minus a. Similarly, for the second portion, I should take f restrict to this subinterval, take infimum, and then look at the length of this interval x2 minus x1. So again infimum of f restricted to x1 x2 times x2 minus x1, and then repeat it further because there are finitely many elements. This is a finite sum. Infimum of f restricted to xn minus 1 xn times xn minus 1. So, for convenience we write this this thing as m0 of f. This is it's starting at a comma x1. So, a is x0, so I am denoting by m0. Here it is n minus 1, so I will be denoting this by m n minus 1. So using infimum we have given some real number for this function and this partition P. One can do the same thing using supremum, that we are denoting as UPF, and we are calling as upper Darboux sum of f with respect to this partition P. So this I know, I think you can guess what this should be. This is summation I is equal to 0 to n minus 1 capital Mi of f. This capital Mi denotes supremum of f restricted to xi minus 1 and xi. So this times xi plus 1 minus xi. Yeah, okay. So MIF is supremum of f restricted to xi plus 1. Yeah, I said the other way. Maybe I added 1. Maybe I reduced the 1 xi minus 1 to xi. No, it's f restricted to this interval xi to xi plus 1. That's what we are denoting by capital MIF. Then I am taking the sum as in the previous case. So now what do we have using supremum and infimum? We have two maps. We have two real numbers LPF and UPF. For fixed partition and for the function f, for the Bonnet function f, there are two numbers in R. Okay. Now I have mentioned before that partition, by definition partition means it is only finite subset of this interval AB having A and B. So even if I put some more elements, some finitely many elements in this set, it would still be partition, because by definition partition means what? A finite subset of AB containing both A and B. Suppose I add some say some element y here, then it is of the how many what is the kernel of the resulting set? Here we have n plus 1 elements. Then if I add say y, I pick some element y here between x0 and x1 and simply write down that here. Then this is also partition, because it is a finite subset of AB, it contains both A and B, but the difference is this has a cardinality n plus 2, previously it was n, now I added one more element. So this is also partition. Suppose I add any finitely many elements, it should be partition. So this process has a name. If I add finitely many, if I suppose we take a partition P, and if I add some finitely many elements to this partition, that gives other partition, let us call it Q. So without y I am calling it P, with y I am calling Q. Then Q is called a refinement of P. So let me write down the definition. So P and Q are two partitions of AB. If P is subset of Q, then Q is called refinement of P. See P we are saying is just a subset of AB. So one can talk about this relation, that P is subset are equal to Q. Now observe the following. For partitions, let me write down this. Okay. For partition we have done two constructions. One is what? One is Lpf, Lqf, Lpf and UPF, right? And then this is one thing that we have done. And the second thing we have done is we have done refinement. So given a partition P, we have a Q, refinement. What is this? take a partition P, add finitely many elements, that is still be finite subset of a comma b containing a and b. So that's a partition. So this process is called refinement. This is what we are denoting by LPF and UPF. So now the obvious question is, okay, fix a P, I have corresponding LPF. For fixed P I have a corresponding corresponding refinement. There may be many. I will pick one. Now the question is, how are these two related? LPF and LQF, how are these related? Similarly, one can ask same question, how UPF related to UQF, right? This Q is obtained by adding finitely many elements for P. Then given P we have LPF, given Q we have LQF, these two are related. Does it imply these two are related? If so, how they are related? Similarly, for UPF also we have the same question, how does UPF related to UQF? So that is the first question. This kind of questions are very common in mathematics. You do two different constructions and then say how these two are related. That is the obvious question you should ask. That is the first set of questions that you should ask. So now let us try to compare LPF and LQF. What is this? Suppose let us for simplicity, let us take a partition with just 3 elements, A, this is B, this is say X, this is P for me. Now what is LPF? I should consider infimum of F restricted to A comma X times X minus A plus infimum of F restricted to B comma X times B minus X. This is what is LPF. Now as I said, Q is obtained by adding finitely many elements to this P. So again for convenience, let us assume Q is obtained by adding just one element for the P. So let me add some elements, say Y here. Now Q is A, Y, X, B. P was just A, X, B. So what is LQF? Again it is infimum of F restricted to A comma Y times Y minus A plus infimum of F restricted to Y comma X times X minus Y plus infimum of F restricted to X comma B times B minus X. Observe that in these two there is one thing that is common. What is it? This part is common, because here I am not making any change, only in the first part I am making some change. So this part is common. So the only difference between these two is here we have infimum of F restricted to Ax times X minus A, here we have something else. Now the question is, can I compare these two? That is the question. So let me write down that Ax Y again, this is A, this is X, this is Y. Now in first case what we have done is we consider the function F restricted to Ax, then we took infimum. Now we are considering F restricted to this and this. So A comma Y is a subset of Ax. So F of A comma Y will be subset of F of A comma X. Now the question is just simply this, can I relate infimum of this and infimum of this? We have done this many times, I think you already know what I am going to write. So the smaller set will have a bigger infimum, because this set might have many other elements, out of them there will be one element that is less than every element here, every element of this. So this says infimum of F restricted to Ay will be greater than or equal to infimum of F restricted to A comma X. Similarly, the same thing for Yx also. So, I have to write down the same thing for yx greater than equal to infimum of f restricted to a comma x. Now, observe that these both of them are greater than equal to a single element. So, I will just write down that here, I will just try to approximate this using the previous observations. So, because these two are greater than some element, so I can take that to be common. So, this element, let me copy paste it. So, this is greater than equal to infimum of f restricted to a comma x times y minus a, the first part. Second part also it is same thing, infimum of f restricted to a comma x minus y. Right, we have already seen just now that this is greater than equal to this is greater than equal to this. So, I am just writing, and yeah, that is all. So, now these two parts have this thing as common, so I can take it out. So, I will just remove this. Now, the result is y minus a plus x minus y. And this minus y gets cancelled, and what you have is x minus a. So, this is equal to infimum of f restricted to a comma x times x minus a. Observe, this is what we have for this. So, this says Lpf is less than or equal to Lqf for this reason that I mentioned just now. Lqf is this plus something, this same thing is common for Lpf also, but this is greater than Lpf. So, this says Lqf is greater than equal to Lpf. Whenever Q is refinement of P, then we have this. Now, once we do for lower Darboux sum, we should do the same thing for upper Darboux sum also, that I am leaving as exercise. Check for yourself what is this, what is the relation between this and this. Because we will be dealing with supremum, again we were restricting it to smaller subsets. So, suppose we take a bigger set and a smaller set, supremum of this, there may be other elements that are greater than every element of this. So, one can do one should do the same thing, and then check yourself what should be this. Now, what? See, so what you have observed is the following, this the relation between refinement and these constructions Lpf and Upf is such that if I take a partition P, if I take a refinement, then Lpf is less than Lqf. So, the lower Darboux sum will keep on increasing if you keep on refining a partition. Once you fix a partition P, keep on adding some elements to that finitely many, then the lower Darboux sum will keep on increasing because infimum supremum are behaved in a, most of the times behave in the opposite way. I think you can guess what should happen for this upper Darboux sum. Here we are dealing with supremum. So, it is this. If you keep on refining the partition, the upper Darboux sum keep on decreasing in this way. Suppose we take a partition P, we take other partition, we take a refinement of P, then for the corresponding partition, the refinement thing Uqf is less than or equal to Upf. Now what? Now one can do the following, one can fix a partition P, take all refinements and then look at the maximum of the corresponding lower sum. So, Lpf is less than or equal to every other refinement. So, one can take the supremum of that. So that we are calling as, say, maybe I do not know, this is very bad notation, but one can do better than this. One can collect all partitions, not just one fixed partition and then keep on refining. One can collect all partitions and then take supremum of those Lpf such that P is a partition. See, one question is, suppose I have a subset of R, should I take supremum or infimum? See, one thing is obvious, if I take a partition P, then we have this observation that if I keep on refining, if I am trying to make it into smaller pieces, then the this lower Darboxam is keep on increasing. So if I take infimum, maybe I'll land just here. So refinement is not really making any difference if I am taking infimum. So the correct thing to do is take supremum, keep on refining, keep on getting a bigger element, maybe there is a particular nice element, a nice partition maybe, we don't really know, because supremum is not like a maximum. So this is what we are doing for and this we are calling as lower Darboxam of F, not with any partition, just lower Darboxam. This we are writing as Lf. I think the idea is clear at least. For a partition, if I refine it, then the lower Darboxam is increasing, so I am trying to take supremum, but for that I do not really need to fix a partition. I can take all partitions and then take supremum of that. That would still make some sense, that we are calling as lower Darboxam of F. Similarly, one can do the same thing by considering all partitions and taking all UPF. I think now you know what I am going to do. We are doing infimum, and this we are calling as upper Darboxam of the function F. So this is what we mean when we write here. Where did you write? I have written somewhere those two maps, right? These maps. For any bounded function, see, boundedness is necessary here because we are talking about infimum supremum. So we do not know how to do it for arbitrary subset of R. Only when I know it is bounded, then I can talk about infimum supremum. So this gave us two maps. One is we are calling as lower Darboxam, one we are calling as upper Darboxam. Now when there, just like in the case of Riemann and Lqf, we have two maps. Where there is a single element that is that takes same value in both these maps. Then we realize that is special, and that specialty is convergence. Same thing, exactly same thing. You take a function F, check for Lf and Uf. If they are same by the previous strategy, this should be treated as special. That special thing is what we are calling as Darbox integrable function. Right. So this is how we define the notion of a function that is Darbox integrable, or we can simply write as integrable. We can ignore that. I mean, not the contribution. I am not saying that, I am saying just ignore the name, because we will have some other integrable functions and those two will be same. So integrable means this or the other thing. So that is why I am saying to ignore this name for now. Now, as I said before, convergence sequences now has two descriptions, right? One is using this Riemann and Lqf, the other is using epsilon n definition. For this you need to mention some element, for this you do not need to mention any element, right? That is the main difference. To say an is convergence sequence, if you are talking about Riemann and Lqf, you do not really need a external element. I mean, here you need to define what is it, but the only condition you need is this Riemann of an is same thing as Lqf of an. Then this element is special in the sense this is converging to this. We also have another description using epsilon n. For this there is some element L belongs to n such that after given epsilon there is a n belongs to n, such that after n belongs to n greater than n, an minus L is less than epsilon modulus of that. So ideally for this there should be some counterpart. So for these maps U bounded on AB to R, U and L. For these two maps, there should be corresponding counterpart in the sense of epsilon n definition, right. That is what we have in the case of convergence sequences. A convergence sequence has two descriptions, one is lim sup in lim inf, the other is epsilon n. So here we have one can think of this as a lim inf lim sup description, so there should be corresponding epsilon n version. So let me write down that. So let us write down for convergence first. So a n converges to A, this means what? Given epsilon positive, there is n belongs to n, such that for every n greater than n, we have mod a n minus L or A less than epsilon. Same definition, I will not change much, see what I am going to do. Suppose f is a Bonnet function, f is said to be nice, I mean we don't yet, we have not seen whether they are same or not, but let me use the word Riemann integrable now, for now. So f is a Riemann integrable if there is a same thing, see, there is a belongs to R such that given epsilon positive, see same thing, there is I cannot say about n belongs to n because this is indexed by n, here we have the notion of what is called partition. So there exists a n belongs to n is replaced with there is a partition P of AB such that for every n greater than n will be replaced here by for every refinement. For every refinement Q of P, something happens. I do not know what to write, what is the corresponding thing here. So something minus A is less than epsilon. Right? If you are trying to copy paste that, we should be writing something like this. Now, to fix the detail here, the notion of partition is not sufficient. We see in case of lim in lim sup, partition was sufficient because we took a partition, then we restricted the function to the subinterval obtained from the partition, then we took infimum supremum both. Now if I am not doing that, we need some alternative for that. So that alternative is what we are calling as a partition with sampling. This only means, yes, we are starting the partition P, say A, B, x1, this is x1, say x2, x3. So we are starting the partition, yes. Then we have extra data also. If you are dealing only with partition, then what we have done in previous cases, we focus our attention to this case, we restrict f2 this ax1, x1 x2, x2 x3, x3b, then we took two elements infimum supremum. Here what we are doing is the following, we take some random element t0, t1 for each subset, t2, t3, and instead of taking infimum supremum, let us simply take value of f at these points. So now there are no two maps, there is only one map, right, and the sum is replaced as follows. So again summation I is equal to 0 to n x I, this is n minus 1, xi plus 1 minus xi. Previously we had two choices, one is infimum, one is supremum. Now the choice is replaced by just taking the value of f at these points. So what is it? It is simply f of ti. So xi to xi plus 1, the choice that I am making here is what I am writing as ti, then I am evaluating f at that point and then simply taking this was same in the previous case also, only this was different. There are two choices, now those two choices are gone into, yeah, we are not taking that, we are simply choosing a sample point and then taking the corresponding image of that point. So this should also get a name. Previously we have called them to be lower Darboux sum with partition P, upper Darboux sum with partition P again. This we are calling as Riemann sum with partition P and sample point T bar. See, this T underscore is to denote that it is not just one element, it is this many elements. Here there are 4 elements. So, if you change n, they will be corresponding. So, 1 for each subinterval. That is what you mean Riemann sum of F for partition P and sample T bar. T bar is to that is the usual notation to say that it is not just one element, it is a collection of elements, 1 for each subinterval. Now we know how to fix this. So, we say F is Riemann integrable if there is element A belongs to R such that for every epsilon positive there is a partition P of B such that for every refinement Q of P and any sampling for any sampling this minus A is less than epsilon. So, this let me fix some name for this we are calling as S P F T bar. So, here we should be S Q F T bar. Q is the refinement of P and T bar is the sampling and this we know SQFT is SPFT. SPFT is this definition. If you refine if you take a refinement of P, you should change this appropriately. So, functions with this property are called Riemann integrable and this A is what is called Riemann integration of F on AB, this element A. And one very obvious exercise that you should think about now is the following. Suppose there may be 2 elements for F, there may be 2 elements A and B satisfying same property. So, can you check whether A and B are same? Check for yourself that A and B should be same. How do you do that? Again, given epsilon positive, there is something, given same epsilon positive, there is something else. Then you can actually say that A minus B is less than. Yeah, I am not going to say the proof. To check for yourself that these two are actually same. If there are 2 elements A and B satisfying same condition, then A is equal to P. This is just like checking the limit of sequence is unique. Suppose I take 2 elements A here. Suppose I take 2 elements A and B satisfying same property, then you know A is equal to B. Same idea, no difference. Here also it is true. So, now what we have 2 notions of integration. One is Riemann integrable, one is Darboux integrable. For Darboux integration, we have used the notion of infimum supremum. So, what we have done is we have taken a partition, then partition by definition is a collection of finite domain elements of the set AB. So, some people call a partition not just the, let me write down that, see this is A, this is B, say x0, x1. So, for some people partition is just A, x0, x1, B, just this set. Some people call partition means they also want to specify this. I mean, it is only if you want to be more careful, you should specify this. So, partition P is equal to the interval A x0, x0, x1, x1b. Some people want to write down partition in this way, some people want to write down partition in just as a set A, x0, x1b, but these two give same description. I mean, once you write this, from this you can write down this, all you are doing is this is an increasing order. So, Ax0 combine, you get the closed interval Ax0, x0 is less than x1, so you take a corresponding interval, x1 is less than b, get a corresponding interval. Again, if you take this, forget about the middle elements, just write down Ax0, forget about the middle elements, write down x0, x1, forget about middle elements, say x1b. So this is only for more convenience. Sometimes this is convenient, sometimes this is convenient. So, depending on the convenience, we use we call this as partition or this as partition. As I said, both of them describe the same thing. Now what? For Darboux integration, we needed 2 maps, just like in case of lim-sup. Darboux integration comes with 2 maps, upper Darboux sum, lower Darboux sum. Then if there is a Bonnet function f, same idea. there also it should be sequence should be bounded sequence to talk about convergence. I am sure you know that convergence sequence should be bounded. So for bounded sequence only we talk about Lpf and Lqf. Same thing here also. For upper Darbox-Sum, lower Darbox-Sum, to define those, we need f to be bounded function. Then we talked about if there is a function f for which uf is same thing as Lf, then we said f to be Darbox integrable. And then Lf or uf, both of them can be seen as the integration of f on AB. Now look at the corresponding epsilon n version. To talk about convergence using epsilon n version, we don't really need f to be the sequence to be bounded sequence, right? What is the definition of convergence using epsilon n version? There is L belongs to n, L belongs to R, such that given epsilon positive, there is some element n belongs to n with property that n minus L is less than epsilon. There is nowhere you can find that n is assumed to be bounded. So to talk about Riemann integration, we don't really need f to be bounded, but see this, I am repeating again and again, it looks like that whatever I have said previously. Suppose n is convergent, then you know n is bounded. Same thing here also. Suppose f is Riemann integrable. See here what I did was I choose some element, some sampling here, that is the extra thing that I have done. Then I have taken FTI. So there is there is no necessity for f to be bounded, right? This finite sum still makes sense. So if f is bounded is not really necessary here. There is no infimum supreme is involved here. So to talk about Riemann integration, you don't really need boundedness. But if I know that a function is Riemann integrable, then the same tricks that we have done for convergence to bounded, we can use same thing to conclude that Riemann integrable implies the function is bounded. So just for to be on the safe side, whenever we talk about integration, we assume that we are in a set of bounded function, and the interval is closed interval AB. Maybe soon you will realize how to extend this to the more general domain, not just the closed interval AB. Yes. So now the next question is, okay, we have done two versions of integrable functions. How different they are? There should not be any difference, because we are just copy pasting whatever we have done for sequences. Lpf and Lqf, the description is same thing as epsilon n description. So here also, if I have a function f that is Darbox integrable, which means uf is equal to Lf, that should be equivalent to the case that f is Riemann integrable. That means there is a belongs to n, a belongs to R, such that this property, what is it? This property is satisfied. Again, if I take a function a f that is Riemann integrable, that means with this property, then I know that the corresponding Darbox integrable property is also satisfied. Now, okay, before we proceed to more to understand more examples or some properties, see, we were doing the same thing that we have done for continuous functions and differentiable functions. What we have done, we take whenever we know that something is special, a function is continuous, then we have checked that given two functions, their sum is special, it is continuous. Given two functions, the difference is special, continuous. Given two functions, their product is special, continuous. Given a function that is non-zero, nowhere vanishing, 1 by f is continuous. Same thing we have done for differentiability also. So we should be doing same thing for integration also. I think so, right? So f and g are integrable on AB, then f plus g is integrable on AB, this being the relation. Similarly, one can just replace this with minus. F and g are integrable, Riemann integrable, then f minus g is Riemann integrable, and this is the relation. One can do the same thing for a product and all that. But see, for continuous functions it was straightforward, but for differentiation we had some surprises, right? For product it was not coming very straightforward. How do you know that suppose you take two functions that are differentiable, then the product is differentiable. It needed some trick. Similarly, similarly 1 by f needed some trick, composition needed some trick. So here also we will do the same thing. So before we are not still ready for to take those surprises. So to make ourselves ready for the surprises, let us write down one result, one small result that might be helpful when we are trying to attack some surprises. So these two are straightforward. F plus g f minus g is straightforward. Maybe fg, it may be still simple, we don't know, we didn't prove it, but we were slightly afraid that something was not straightforward for differentiability. So we are preparing, maybe we are preparing more than what is necessary, but we will just prepare it. So very small result we will do it, then we will stop. Next session we will do the other results, that product, composition, 1 by f, whether it is integrable or not we don't know, we will see that. Then we will see some examples. Whenever we know how to construct some whenever we know this algebra is matching properly, then there are many ways to we can construct more functions from old integrable functions. That is what we have done for a case of continuous functions and differentiable functions. So once we know that f plus g, f minus g and all these are giving integrable functions, then that gives some peace of mind that we can construct more functions from old integrable functions. So further we will do some the following result. Let us take f to be integrable, Darboux integrable, which means what? Uf is equal to Lf. Right, this is Uf and Lf are defined using infimum and supremum. I forgot what is Uf. Let me check. How did we define Uf? Is it supremum or infimum? Oh, we didn't write that down. Lf is supremum, so Uf should be infimum. Right. Uf is the infimum of U Pf for every partition P of AB, of course. Similarly, Lf is the supremum of L Pf, P is partition of AB. Now see, whenever you will see infimum supremum, if you want to understand more, how do you understand more about infimum supremum? You apply the first rule. What is first rule? Suppose you take infimum, you have some bonus subset A. Suppose this is L. Suppose L is infimum of a set A. Then if you take any element that is greater than L, this resulting is not a lower bound. That means what? There is some element that is less than that and still contained in the set that you are talking about. Suppose we are dealing with A subset of R and L is infimum of R. If I take epsilon positive and take L plus epsilon, then this is not a lower bound, which means what? There is some element A belongs to A such that A is less than L plus epsilon. Similarly, again for the same thing A, maybe you can take L is already used, so let us take M N P. Suppose P is supremum of A, then what? Suppose I reduce the here I have added some element, so here I am taking P minus epsilon. Suppose I take some element less than that, then this is not a upper bound of A, which means what? There is some element I used A here, I am using B. B belongs to A such that P minus epsilon is less than B. Right? Whenever you see supremum infimum, not just in this course, maybe in later course also, whenever you see infimum supremum, the first thing you need to do is you do this kind of thing. That maybe this thing can give you a easier result, better understanding of those two. So now what do we do? Let us take epsilon positive and look at UF. This is for infimum, so UF plus epsilon. So UF plus epsilon infimum, right? Yeah, UF plus epsilon. Then what? According to this, there exists an element here, a partition, such that UPF is less than that. So let me write down that. So U some partition F is less than. equal to is not allowed, less than that. So, to mention that it is coming from epsilon, let me denote that by epsilon, p epsilon f. One can do the same thing for Lf also. Lf is supremum. So, if I take an element less than that, so Lf minus epsilon, then this is not an upper bound. So, there is some element here, that means a partition such that that partition f is greater than this. So, it is less than L Pf. Again this is dependent on the epsilon, so I should mention that epsilon. See, we are using same thing for both, but it is not necessarily true. So, to differentiate, let us mention that it is coming from p epsilon is coming from u when you are doing the upper Darboux sum. This is the L lower Darboux sum, right. Now, but see, expecting that this is these two are same, maybe slightly too much, maybe slightly too much, but one can of course do the following, that given two partitions, this is again partition of AB, this is also partition of AB, one can combine those two partitions and get a new partition, right. Let me write down that. So, A, B, suppose AXB is a partition and A by B is a partition, one can simply take the union A, X, Y, B is a partition. This kind of thing is called common refinement. So, the resulting thing is a partition for both AXB, resulting is a refinement for both AXB and AYB. So why am I doing that? So let us take p epsilon is a common refinement of this and this. Now what? I should go back and check. So p epsilon is a refinement, means what? This is contained in p epsilon of u, contained in p epsilon of L. Now, if Q contains P, then we know what is the relation between Lpf and Lqf, right. What is it? Yeah, if P is contained in Q, Lqf is greater than Lpf. So, let me copy paste, I might forget, because again I have to prove it again if I have to use it there. Let me just copy paste this here. So, P is contained in Q, so we have this. So, here I should just replace this with P epsilon u, and this I will replace with P epsilon. Yeah. Now, in case of upper Darboux sum, it is reversed. So, this is the u, if I take this to be u, then this should be reversed. Now, q is now p epsilon, this is again p epsilon of u, okay, this is L. So now we have these two inequalities, Lp epsilon f is greater than this, UP epsilon f is less than this. Now, using these two, let us try to give some relation between this and this. So, let me first copy paste this. Now, see, observe that I can get rid of this to push it here. So, u p epsilon u comma f is less than uf plus epsilon, that is less than see uf is something as Lf, because we are dealing with integrable functions. So, this is actually equal to Lf plus epsilon. but Lef is less than this plus epsilon. So, there is a extra epsilon. So, this is less than L p epsilon L f plus 2 epsilon. See, the only problem was these two are not same, that is the problem. So, now we can get rid of that also. How? Observe here that L p epsilon L f is less than this. So, one can of course write L p epsilon f plus 2 epsilon, right. This thing is less than that. Now, we have one more thing, we have u p epsilon f is less than this. So, one can write down something before this. So, u p epsilon f is less than or equal to. So, now what do? We have for a fixed partition p epsilon, we have an inequality. This is less than this plus 2 epsilon. So, u p epsilon f is less than L p epsilon f plus 2 epsilon. Now, we know, we have seen that before many times also, 2 epsilon is as good as epsilon. So, now what we have, given epsilon positive, there is a partition such that UPF minus LPF is less than epsilon. This is useful. We will see the use maybe later in the next session. This is useful to prove at least to prove that the other algebra is matching properly. This will be useful, and also to prove other results. That's all for today. In the next session, we will see some algebra and some examples, and one result about integrable functions. That's all for this session.